Hey everybody. So last time we talked about main sequence stars and how what makes them a main sequence star is that they're stably fusing this hydrogen into helium. And so the core is being squeezed by that envelope, the outer part of the star, and it's generating its energy through nuclear fusion. So what we want to talk about this time is how does that process work? What is it that's making this thing squeeze together, and why does the star stay stable so that it can be a main sequence star? So that's what we're going to focus on in this one. Let's get started. Okay, so as I said, we're talking about star structure today. Go ahead and have your class notes out as always. This is going to be tool 15. Looks like this. Front and back on both sides. So go ahead and pause the video until you've got that out and you've got it ready. Okay, so our big question basically is, why does the sun shine? And the answer to that is through nuclear fusion, but there's a few things we have to talk about before we can get to that point. So hydrogen, which is what most of the universe is made out of, is nothing more than a proton with an electron going around it. So now we're not going to worry about the electron quite so much. That's what's producing those lines when it jumps in the absorption spectrum when it jumps up and down. Now we're interested in the proton itself. Now, if you remember from high school, each one of these protons has a positive charge. So think about magnets. Do like charges attract, or do opposites attract? Well, if you think about your relationships, you probably know that opposites attract. And if you're too much like each other, then you're going to repel each other. And that's exactly what's happening. These protons don't want to come together. So the atoms, if I have a whole bunch of protons, together making up the nucleus, they should all fly apart. Nothing should be holding them together with that. And this would be the case if the electromagnetic force were the only force that were involved. So there's four basic forces. We've talked about the electromagnetic force. Those are magnets that are repelling or attracting or whatever. Then gravity, of course, is going to cause things to come together. Gravity is very, very weak, so it's not strong enough. Gravity isn't strong enough to overcome the electromagnetic force that's pushing these things apart. Then the other two forces, one of the other ones we're going to talk about is the strongest force in the universe. It is stronger than any of the other forces, and it's called the strong force. Yeah. Physicists need to get out a little bit more. They're not terribly creative in their naming, but it's called the strong force. Now, the strong force is stronger than the electromagnetic force. It's stronger than gravity. It's stronger than everything else. So, but the problem is that it's very short range. So only when these things are very close together, when these protons are very close together, the strong force can take over and hold them together. So if I've got a big fat atom like this one that you see here, the red ones are protons, the black ones are neutrons. They have no charge whatsoever. So these are all positive charges. They should all fly apart. But the strong force that the neutrons are adding and the protons are adding are keeping everything together. But the strong force is pretty much the same size as this nucleus right here. So this neutron over here just barely feels the force from this proton over here, and so on and so on. So this thing is very unstable. It's hard for it, it doesn't take anything more than a little kick, and then the atom will actually fly apart. This is nuclear fission. This is how Palo Verde nuclear power plant, things like that work. This is a radioactive atom, so like uranium or something like that. So we've got this atom that's very unstable. We give it just a little bit of kick and it breaks into two smaller atoms. Well, the mass of these smaller atoms is less than if I add them up, this plus this is less than the total mass here. We've lost some mass. Well, that means I've got to have gained some energy somewhere, because if you remember Einstein, you've probably heard E equals mc squared. That just means that mass and energy are two forms of the same thing. It also means, though, since c squared is a big number, a tiny change in mass is a huge amount of energy. This is why Palo Verde produces a huge amount of energy, because it takes that uranium and splits it, and even though the difference here is tiny, the difference between the sum of these and the total mass that start out with is tiny. When you multiply that by c squared, it's a lot. And so you get a lot of energy out of that. Now, in the case of fusion, though, we're going the other way. So here I've got two protons that do not like each other. They do not want to be together. If I can get them to stick together, if I can push them close enough so that that strong force takes over, the strong force will take over, it'll bind them together. And then what I get is a helium atom. So two protons, two hydrogen atoms will make one helium atom. And so when these things fuse together, the difference in mass is still very small, 0.7% or something like that. But it's still very small. But again, you multiply by that c squared, and it's incredibly huge. Fusion is what's powering the sun. So let's look at what happens in the energy generation from the sun. So in the core of the sun, we take 4 protons and we squeeze them together. Now remember, these protons do not want to go together. So it's like, if you and your mate are too much alike, then you don't want to get together. What you need is that overbearing mother-in-law who says, "Bon, honey, you're so good for each other," right? And she pushes you together. And then finally you get close enough to where the strong force takes over and you bond and you make baby energies and all this other sort of thing, right? So we need the entire mass of the star, the entire envelope of the star, to squeeze hard enough to get just the core to force those protons together. So I take 4 protons, go in, and what I get out, so this is 4 hydrogen atoms, I get a helium nucleus, which looks like this, and a couple of gamma rays, some positrons, that's antimatter. Yes, there is antimatter actually being made in the sun, and some neutrinos. Neutrinos are tiny subatomic particles that have almost no mass. They can pass through almost anything. And if you saw that terrible movie 2012, the idea behind it was that the sun's neutrinos can penetrate the rock of the Earth, and they do. And so they were heating up the Earth's core. And so then the core was causing the ground to melt, and this is what was destroying the Earth and that sort of stuff. Yeah, no. Because, yes, the neutrinos can go through the rock of the Earth. They can also go through the friggin' core of the Earth. So they're just not going to have that effect whatsoever. There's nothing that's going to cause them to heat up the Earth or anything like that. They just keep on passing through. But this is how the energy from the sun comes out, through gamma rays. Positrons then, these anti-electrons, combine with a normal electron, and then they release energy. So like anytime I have matter and antimatter, when I bring them together, they explode and they release a lot of energy. So this is basically energy, and then those neutrinos are carrying energy as well. That is where the heat from the core of the sun is coming from, and that might be 10 million degrees or so. The total mass is 0.7% lower. That's not a lot, but if you multiply that by 3 times 10 to the 8th and then square that, you can see that this is a lot of energy that I'm getting from here. And so the sun has been a continuously exploding hydrogen bomb for the past 4.5 billion years or so. So we talk about we need to squeeze that down. And even though it's just gas does squeeze. And so this is the atmosphere that we're seeing here. This is an analogy with pillows. If you take pillows and you stack them up, those pillows, even though they're just, light squishy pillows, those bottom ones are going to get flatter and flatter and flatter as I add in the weight. And so just the weight of it's going to compress, and I add another one and it'll compress. And so the same thing is happening in the atmosphere. Just the weight of the gas makes it so that it's compressed and thick enough for us to breathe down here, all this nitrogen down here. So this is another example, and you see the girl on top kind of has it made. She's like, yeah, whatever. But this guy on the bottom has to endure the force of both of these guys pushing down on him. So it's the same thing that's going on. But I need the entire mass of the star's envelope, that outer part, to squeeze just the core enough to fuse. So we're going to talk about a 2-part model for the star, and this is the model we're going to use for the star from here for the rest of the course. If you ever do decide to major in astronomy, you're going to figure out that there are different layers in the stars and things like that. But for our purposes, we're going to talk about the core, and that's where that energy generation, where that nuclear fusion is taking place. And then the atmosphere is what's squeezing that. Okay? It's energy balance, so the energy pressure, if the star is stable, the pressure from the energy pushing out is equal to the weight pushing back, trying to cause it to collapse. Let's see how that works. So this is on the back side of your class notes here. So, and looking at what it says underneath, suppose the energy is too strong and it pushes the envelope outward. Okay, so let's suppose for some bizarre reason, the sun is putting out too much energy. So it's exploding harder. So all that energy is causing the gas to move outward of the envelope. So, but as that pressure is relieved, if I'm not squeezing as hard, then what happens to the fusion rate? Well, if I'm not squeezing as hard, I'm going to have fewer of those protons coming together. So my fusion rate goes down. Well, if the fusion rate goes down, I'm not getting as much energy. So the energy rate also goes down. So now let's think about it. The envelope is out here, and all of a sudden the core's gotten cooler. Well, what's going to happen to it? If the core is not pushing out as hard, if the core is not producing as much energy, then it's going to settle back down. You see that? And so even if for some reason the energy got too high, the energy will drop down because the core is pushing the envelope out, and then the envelope will come back to where it's nice and stable again. So again, looking at this, let's suppose that the energy is too weak for some reason, and so the core, the envelope is now starting to fall inward. So for some bizarre reason, the energy in the core is too weak. And so the weight of gravity makes everything fall towards the middle, so that gas falls in and it's squeezing harder. What's going to happen to the fusion rate in the core if it's squeezing harder? Pause the video, circle your answer. Right, if I squeeze harder, then that means the fusion rate is going to go up. I'm pushing more of those protons together. Well, every time I push those protons together, I get some energy. So what happens to the rate of energy generation? Pause the video, circle it. If I'm pushing more of those protons together, I'm going to get more of that energy from that. So I've got more energy coming out. So what's going to happen then to the envelope? It was squeezing down. What's going to happen to the envelope? Pause the video, circle your answer. Okay, well, as that energy picks back up, it's going to start pushing the envelope back out. So it's going to stop that collapse. It's going to start pushing out. So this acts as a thermostat that keeps the sun stable. So let's suppose that we get a slight rise in temperature, like we're saying here. So we're getting little too much energy. This leads to a large increase in the fusion rate, which raises the core pressure. That pushes the envelope out, and the core starts to cool down because we're not squeezing quite so hard. And so we come back to our normal temperature. If for some reason I have a little less energy, then there's a decrease or a little less temperature, then I decrease the fusion rate. That lowers the pressure in the core. It's not producing as much energy. So then that envelope starts to contract a little bit. Well, as it contracts, it increases the fusion from the star in the core, and we reach that balance point again. So the sun has been sitting here perfectly balanced in what we call hydrostatic equilibrium. You don't have to know the definition of that word necessarily. Just hydrostatic means it's balanced. Hydrostatic equilibrium means it's balanced. So the sun is an exploding bomb, but there's enough mass to actually hold that together. And because of the way the two feed each other, if the sun explodes too hard, well, what's making it explode is that mass. So it pushes it out, and now the energy generation rate goes down, so we're balanced again. If for some reason it's not exploding hard enough, then the core collapses, or the envelope collapses, squeezes harder, and that rate goes back up. And so we stay nice and balanced. So the sun has been here for 4.5 billion years. It's probably got another 5.5 billion years or so left to go. We discovered the composition of the sun that was made from hydrogen and helium because of the work of Cecilia Payne. Now, Cecilia Payne was one of the first astronomy PhDs in the world. She was actually given grunt work by her professors. Women were not treated very well in science at this particular time. So he said, well, okay, here's the spectrum of the sun. And you can see it's this rainbow with these lines here. And we know what the sun's made out of. It's going to be made out of the same thing as the Earth. It's going to be made out of silicon rocks and metals and things like that. But, you know, you're a woman, so let's have you go off and do this work that the men here don't really feel we need to be doing, right? So she gets in there and she says, fine. And so she looks at it and she discovers, nope, you are all wrong. The sun is almost entirely hydrogen and helium. And it was her work that enabled us to figure out, oh, if the sun is hydrogen and helium, then it must be powered by nuclear fusion. So Cecilia Payne's work then is responsible, her work with this absorption spectrum is responsible for everything that we know about stars and how it works. So ladies, don't ever let a guy tell you that you don't know what you're doing, because women are the ones who are ruling science right now. All right, so in summary then, stars generate their energy through nuclear fusion, through squeezing those protons together. Hydrostatic equilibrium is that thermostat, it's that balance that's keeping everything the same. And so that balance is keeping the star stable. Remember, what is the definition, what is a star that is stably fusing hydrogen into helium? That's a main sequence star. So what we're talking about is what's powering these main sequence stars. The sun and most other stars are 73% hydrogen, 25% helium, and 2% other stuff. And that stuff is what's left over to make planets and puppies and kitties and unicorns and you and me and all that. Okay. All right, so download the Star Structure Practice Worksheet. Looks like this. It's pretty quick and easy. It's just basically reviewing the concepts that we've talked about here. And then submit it. It'll be graded for accuracy as always. Okay, so now you know how it is that stars shine. They shine through nuclear fusion. They shine because it's got that hydrogen that doesn't want to come together, but if you get it close enough, it'll fuse into helium, and that will actually release just a little bit of energy that gets converted into mass. But remember that that doesn't want to happen on its own, and this is going to be important when we talk about how stars die. But those two things don't want to come together. You need the weight of that envelope, that overbearing mother-in-law to say, "Bon honey, you're so good for each other," to squeeze down and keep those things going. That squeezing then is what's keeping the star stable. It's keeping that balance. Squeeze too hard and the energy goes up, which pushes the envelope back out. Don't squeeze hard enough, the energy goes down, and so then the envelope comes back. So it stays nice and balanced and stable. All right, so that's it for this one. We'll see you next time.